Greetings, hackers. Glad to see you again. Today we are talking about write-ahead logging. This is a technology which makes a database reliable. So first thing when you when you store your data, you want to store your data. You don't want to lose your data. You want your data to be in a safe place. And when you access it, you want to access it reliably. And safety of your data is a very important for database. But when database client commits transaction, and we report him that transaction is committed, we have to move data of this transaction to some permanent storage, non-volatile storage, which will survive if power will be lost, or if operation system fail, or if other hardware fail. And usually this device is quite low on this hierarchy. So you have a fast main memory, but it's energy dependent, and power lost, and cord is unplugged, and everything that was in your random access memory is lost forever. Then you have hard drives. Sometimes they are mechanical, sometimes they are solid state drives, but still accessing hard drive is slower than accessing main memory drive, and you want to minimize count of operations you do on your energy independent drive. And you want to organize all writes in order and make them fast while retaining ability to have a complicated indexing structures in your fast and energy dependent memory. To solve these tasks is used the technology which is called ARIES. This is an acronym for Algorithms for Recovery and Isolation Exploiting Semantics. In theory, we have a write-ahead logging. This means that every change to database is written in an ordered way to a non-volatile, energy-independent device. Then you have functions to repeat history, making a redo, and functions to do undo. To undo your redo that you made earlier. So, in theory, ARIES allows you to make reliable recovery. You can have a second crash of your database while you apply your write-ahead logging, and it still will be okay. Your database will be fine, but it's too complicated. On practice, we have just login changes and the functions to apply these changes. And we have a snapshot of our database. It relies somewhere on disks. And then we gather some write-ahead login files which contain changes to your tuples, changes to your pages, and all them have to be written without any buffers to permanent storage where they can live for a significant amount of time and where they will survive crashes, power crashes, or operation system crashes, etc. By default, you have to use full page writes in your write-ahead logging. This means that when you modify a page after a snapshot, you make a full copy of your page. This is necessary when your file system do not provide you a capability of writing a page in a single transaction. If you can modify just a part of your page, this feature have to be enabled. But on some file systems, you have atomic page write, and you can have this feature disabled, full page write disabled, and you will have a write performance slightly higher, you will have less write-ahead logs. But why do we study this at all? This is a course about data access methods. Because as a data access method, you have a developer, you have to implement WAL features. This means that if you want your index to be transferable through write-ahead logging, it has to have some important parts. First of all, your index creation handler will have to supply a function which will replay log files on your index. And second, after every change in a page, you write specific code which adds history of your change to a log file. Here you see example of forming log record to val. First you check whether your index needs to be valid, and then you create some data chunk which describes what exactly have you changed and where have you changed. You pass the buffer to your function, and then everything about your change will be logged. Now let's talk a bit about what else do we have besides recovery, besides reliability, by having a write-ahead log.